Okay. Okay, in this lesson, we will start studying integrals and, as you will see later, differential equations that are closely related to this idea. And the idea of integral is connected, is one of the two starting ideas of differential calculus. We said that the first idea is the idea of derivative, and the derivative is what? Is the generalization of the problem of finding the tangent line to a general graph, not only to an elementary object or geometry like circles and so on, but to a general graph. The idea of integral, again, starts from a similar question, that I have to move from elementary situations to more general situation. What is the idea? Is essentially computing the area of subsets of R2, subsets of R2. And everybody knows that elementary geometry gives us the rules for computing, for instance, the area of a square. We know the measure of L squared, or a rectangle, or a trapezium, or a circle. Okay? Then the same problem arises here. Suppose I have the graph and consider a positive function. Okay, positive, bigger or equal than 0. And this positive function in an interval AB defines a subset of the plane. Okay, a subset of the plane that is included between the line x equal A, the vertical line, the line x equal B, that the other line, the x-axis, y equals 0, and the graph of the function. Okay? And I'm speaking about a positive function. Then you can define that is this region of the plane. And this is called, in general, the trapezoidal region. And we write T, F, A, B, okay? Function F in the interval AB. And the problem that started, one of the two problems that started differential calculus and integral calculus is, can I give a rule for computing the area of this region? Okay? For positive functions, or we will see in general. Now look only at this elementary presentation, then we will see all the details. And the problem has been treated in different ways, okay? And essentially, we have three definitions. Really, there are more. But the main ideas for defining integrals are given by Cauchy, as usual. That was in about 1820. And he gave the theory of integration when my function f is continuous. Riemann, about 30 years later, in 1850s, gave a more general approach that requires only the function to be bounded, but not necessarily continuous. And also this proved not to be sufficient for mathematics. And around the year 1900, Henri Lebesgue, French, gave a more general definition of integral. And this is related with the so-called measurable function. And this third approach cannot be treated in this course. In the textbook, you find separately the Cauchy approach and the Riemann approach. We have no time for both of them. I will give you the main ideas of Riemann approach in a moment. Okay? And then, let's say first, what is the idea, and then we pass to technical questions. And the idea, you can see from this graph. We have, for instance, you say here, I have the function x squared in the interval 0, 1, okay? And I want to say, how can I measure the area that is below the graph, above the x-axis, in the interval 0, 1? Okay, and the starting idea is, I don't know, in general, this is not an elementary formula of Euclidean geometry, okay? The formulas of primary school, junior high school. And the idea is we try to find an answer to this question with the idea of approximating. Okay, I use the idea of approximation. Then I try to approximate this region. Okay, I don't put a color in this region because it will be confusing in the next steps. But when I say the region is below the parabola, above the x-axis, in the interval 0, 1. Okay, and the idea is I approximate with functions, okay? With functions, which type of functions? The easiest possible functions. And the easiest possible functions are constant functions, okay? And then I say, I want to approximate first, I will do this approximating this region, okay, this function, by below, then from above, with constant functions. Why constant functions? Because if you take a constant function, the trapezoidal region of a constant function is a rectangle. Okay? And then I say, I want to approximate from below this region with rectangles. If I take the interval 0, 1, okay, you see that I cannot put a rectangle that is below this graph, because the rectangle should be, the eighth of this rectangle should be 0. But if I say I divide this interval into two parts, I divide into two parts. And then what happens into two parts? I can say in 0, 1 over 2, the approximation of my function by below is 0. But from 0.5 to 1, I can construct what? I can construct a function whose value is 1 over 4, since my function is x squared, and then I have this rectangle, okay? And then I say the area of my region may be approximated by the area of this rectangle. Okay, that's clear? This rectangle, the area is 1 over 2 times 1 over 4. Then this area is 1 over 8. What happens if I move? And now I decide I don't want to divide into 2 parts, but in 3 parts. Then if you divide into 3 parts, you see that what you can do. You can approximate the first part with the constant 0, the second part with a rectangle of this type, and the third part with a rectangle of this type. Okay? And then the idea is very clear, I think. I can do this increasing the number of subdivisions. Okay, now I increase the number of subdivisions, and as you see, what I get? I get a finite number of rectangles. Okay, I get a finite number of rectangles. If I compute the area of this, plus the area of this, plus the area of this, and so on, I get the area of this region that you see in blue, okay? This region, and it is very easy to understand, the area of this region will become quite closer, a little closer, to the area of my trapezoidal region, okay? That is the area below my graph. And the idea now is this. I increase the number of subdivisions, and when this number increases and increases, okay, the blue region becomes closer and closer to the trapezoid that I want. Okay, and then you understand here what is the starting idea. The starting idea is take the interval, divide the interval, okay, construct this function that approximate my given function by below, okay, and then do what? Take the number of subdivision become greater and greater, and then we know that this means take the limit when the number of subdivision tends to infinity. Okay, that's the idea. Is that clear? Okay. If you do the same, you can do the same also from above. Then if I cancel this and see this, from above, what happens? I have to find a rectangle in whom my region is included. Then the first step is this big rectangle, whose 8 is what? Is the value of the point of the function at the point 1. Okay, that is what is for my function is the maximum value. If you divide into 2 parts, you can see that the approximation in the first half, decreases. And see, this, I don't know why it doesn't work, but when I take this n, okay, take n equal 2, okay, you see that now you can approximate from above my region with a lower rectangle in the first half, and again the big rectangle in the second part. If I divide in 3, okay, if I divide in 3 parts, 4, 5, so on, you see that the approximation from above becomes better and better. Okay, Now, my region is always included in these rectangles, okay? And then a good approximation for the area I want is what? Is the sum of the areas of the rectangles, okay? Then if you look now at the numbers, at the beginning I have what? From below I have 0, because the rectangle is just a line. From above I have the big rectangle, area 1. When I divide into two parts, the area of the lower part increases, the area of the upper approximation decreases, and then, okay, this was, then look at the numbers. Then in the next step, I have n equal let me confirm the object properties. Okay, n equal 2, you see, the number now in B, the lower, the blue increases, the red decreases, okay? And when you move to higher values, you see the blue number increases, the red decreases, and they become closer and closer, okay? In a very slow way, but they become closer and closer. And then we have this idea for the computation of integrals. Okay, then you can see in this case, if you look at the blue rectangles and the, let's say, red rectangles, you see that the difference between their areas has become very small. It's just this plus this plus this plus this plus this. Okay? Then this is the main idea for integrals. I approximate a function with constant functions. Okay? And I approximate the measure of the area with areas of rectangles. And the areas of rectangles are known from the elementary geometry. Okay, that's clear. And now we do this from the formal point of view. Okay, I said the first thing is given a function, I define the trapezoidal region. If the function is positive, is what you see here. If the function is negative, you have to take the region that is bounded by x equal a, x equal b, and now by the graph of the function below, and y equals 0 above. I have this region. When the function has both signs, the trapezoidal region will be this and this. Okay, the combination of the two. Okay, then my idea is that I want to associate to the trapezoidal. That is what we are, the end of our work. I want to find a procedure such that to a trapezoidal region, I will associate a real number. Okay? A real number. And this will be the integral. fine? The meaning of this real number will be, if my function is positive, this real number will measure the area of T, okay? If my function is negative, we'll measure minus the area, okay? Will be the area with negative sign. Remember that the area geometry is always a positive number, okay? And if the function has different signs, we will see later what will be the meaning of this number, okay? We will see in a further step, okay? And then we start saying, given a function, I said I approximate this function with functions that are constants, okay? Constant in each subinterval. And then I must give first this definition. Given an interval AB, I consider points x0 and so on with this rule. The first point, x0, will be A. Then I will choose x1 bigger than x0, x2 bigger than x1, the ending with a point xn that will be B. Okay? When I do this, that is given A, B, I choose points. x0 is A, xn is B. For instance, here I choose x1, x2, and x3 is B. Okay? This will be called a subdivision of my interval AB. Okay? Or also a partition of AB. Okay? And fine. And a step function is what? Is a function f defined in AB with values in R that has these properties, that given a partition, then I have to start with a partition, and then I construct a step function such that given a partition x0, x1, xn, and given n real numbers, n numbers, C1, C0, no, C1, excuse me, Cn, my function has the value f at the point x equals ck for all x belonging to xk minus 1 xk. Okay, this seems to be a quite involved definition, but let's see my example here. I have the first point A, the point B. A partition is x0, for instance, x1, x2, and x3, that is B. Okay? I need 1, for in my case, n is 3, my example. Then I need C1, C2, C3. And what is the definition of fx? My function f of x is C1, okay, read here, C1, for all x included in x0, x1, okay? Then this means that my function in the interval x0, x1 has a value c1. Then in the next interval, c2 will be the value between x1 and x2, will be something of this type, and c3 will be, okay, the value in the third interval. That clear? Then I divide my interval and I take a function that is constant, okay, constant in each sub-interval. Okay? And a question immediate. And at the points x1, for instance, this definition doesn't say what is the value at x1. Okay? And then I say I can choose what I want in this point. And we will see that this is not important in this. Okay, then in the open intervals is a constant. In the points, you can choose the value you want. That's fine? Okay? Okay, for a function of this type, I can define the integral. What is the integral? If I want to give the idea, these are positive constants, okay? If you want to give the idea of the area that is below this function, what can I say? The integral will be the area of this rectangle plus the area of this rectangle plus the area of this rectangle. Okay? Then I can give this definition, okay? If my function f belongs to the set, as there will be some symbols in this, S is the set of step functions on AB. Okay, the set of all step functions on my interval AB. Then, definition. I will call integral over AB of a step function f simply what? Simply what is written here. Okay, what is this? This is the product. The area of these rectangles are what? Are these numbers, C1, C2, C3, each is multiplied by the length of this interval, okay? And the area of this rectangle. Then, in general, this will be what? Will be the sum when k ranges from 1 to n of the ck, that are the values, the constant values, times the length of the segments. And the length of the segment is xk minus xk minus 1. Okay? Then, if yes, then if these constants are all positive, fine. If you have all positive constants, you have what? You have exactly the sum of these areas. If the constants are negative, each term of my sum is what? Is the area of the rectangle that you can see below the graph, for instance, like this, is if the constants are negative, the product of this constant, negative, times the length of this interval is not the area of this rectangle, but is minus the area. Okay? Then, if the constants are positive, we measure exactly the area. If the constants are negative, we measure minus the area. Fine. If some are positive, some are negative, is more difficult to say, because some are taken with the positive sign, some are taken with the negative sign. Okay. And this is the first definition. And then I say, okay, I know what happens for step functions. And there is an immediate property. If I have two step functions, f1 and f2, if f1 is smaller or equal to f2, then, I think this is quite immediate to understand, the integral AB of f1 is smaller or equal to the integral of AB of f2. Okay? And now I want to go back and to give the idea, of what I did here, or what I did in this example. Okay? Then what is a step function now is given, the idea. And then we know that the blue region is the trapezoidal region of a step function. And also the other region, okay, let's say red region, is the trapezoidal region of a step function. Now, what can I do with, now I'm considering a function f of x. And then what can I do now is the following. I take now a function f that is bounded on AB. Okay? And I do what? I consider this set. I consider this set. I consider the set that I call S plus of f. What I'm doing now is the formal definition of what you saw before, the step function that is above the graph. And I say that in this set, I will put what? I will put a function h that is a step function, okay? Is a step function with this property. With the property that h of x is in each interval defined as what? If you go back to the picture, if you go back to the picture here, what happens here? That in each sub-interval, what is the type of function that I choose in each sub-interval? For the, now I'm considering approximation from above. In each sub-interval, I choose as a step function the function that, what is the value of this constant? Is exactly the maximum, okay, of the function x squared in the subinterval. Do you understand clearly this? In this subinterval, this, the value of my step function is this. And this value is the maximum. Fine. In the other interval, the value is this, and the value is the maximum. That clear? Fine. But this is what? This is a continuous function, because the example is x squared. If you consider a bounded function is not necessarily continuous. Okay? And then I cannot take the maximum. Okay? I take the supremum, the sup. And then I have to take the sup when x belongs to the subinterval xk minus 1 xk of the function f of x. Then in each subinterval, I take exactly the sup. Okay? And in the other points, in the point x1, x2, x3, I can choose as I want. H of xk should be bigger or equal to f of x at these points. Okay? And the points of the subdivision, you choose what you want by bigger than the function f. And then this will represent the step function above. What I do on the other side, I take the set of functions g, step functions on AB, such that g of x is the inf of f of x in each subinterval. Okay, in each subinterval. At the points xk, I can choose as I want, but smaller than f of xk. Fine? Then, if I do this, what I get is what? Is that if this is a subinterval, you have your function in the subinterval, bad graph, in general. You get your function that in general is not a continuous function in the subinterval. And what I did, from below, I choose the inf as a constant. From above, I choose the sup as a constant, okay? And then I have a step function below and a step function above my graph. And this will be the same for all the subintervals. Okay? When I do this, what can I do? Now, the final step. The final step is what? Then, here you see the step function that approximates by above, from above. Okay? Here you see the one that approximates by below. Fine? And then what I say? I have to do now what? I have to change this number of subdivisions and let this become greater and greater. Okay? And now, please, there is the difference. For my computer program, I choose the subdivision as I divided the interval in the subintervals of the same length. Okay, all these are equal. You have to imagine that this is not necessarily, is not in the definition. I can take any partition I want. And then, what is the idea? The idea now, I take all the approximating function from above. That clear? I compute then, I compute the integral. I compute the integral of the function h for all h belonging to S plus, then the green. Then you imagine given the function, I took a subdivision, I constructed the green function, I computed the integral of this, okay, and I did this for all functions of this type. That means for all partitions. And in this quantity, I take all the possible integrals, and since I'm moving, I am above, I'm interested in the minimum possible, because approximating from above, I'm going to lower values, and then I take the infimum of this function. Okay? And this will be called, there is no space here, I write here. This, I write this as integral AB with a bar over the integral, and I call this upper integral of f on AB. Okay, this will be the upper integral. Then I do the same for the functions g belonging to S minus, that are the functions that approximate by below. And for this case, I am interested in increasing as possible this. And then I take the supremum. And this will be called, the symbol will be integral AB f with a bar below. And this will be called the lower integral of f. Okay? Then, all the possible step function above, I compute the integrals, and I take the inf of this. Then, from below, I take the sup of this, and now what happens? It happens that in general, what I have? I have that the lower integral of f is smaller or equal, the lower integral is smaller or equal than the upper integral, okay? Approximating from above, give me a value that is bigger what is for this picture a value of an integral of a step function from below is a red number. A value from above, sorry, the opposite. A red is a number that approximates from above. This is an integral that approximates by below. When I change this, okay, you see, one decreases, the other increases. And I am interested in the inf, okay, or the sup. Then the sup of the blue, fine, and this is the lower integral. The, excuse me, yes, the sup of the blue is the lower integral. The inf of the red will be the upper integral. Okay? And the lower integral is always smaller or equal than the upper integral. And then, definition. If, what happens? The lower, I said that the lower integral is always smaller or equal to the upper integral. Then I can say that if, then definition, if the lower integral equals the upper integral, we say that f is integrable on AB. And sometimes we call Riemann integrable, to remember that we are using the Riemann approach of the integral. And we define the integral AB of my function f as the common value of the lower and upper. Okay, if the two are equal, if the two lower and upper are equal, we can say that the common value of this is the integral. Okay, and that is the definition of what is a Riemann integral. And the first question is, okay, I hope you understood the idea that approximating below above, if the two approximations give the same number, this is the integral. But the idea is, okay, this is always true. When there is equality, is integrable. But the question is, is it possible to find function for which there is no equality? Okay, there is a strict inequality. In other words, there are functions that are not Riemann integrable. That's clear. Because if you think about, for instance, a continuous function, seems to be quite immediate to say, okay, the two approximations for becoming the intervals smaller, smaller, and smaller, they give the same result. It's reasonable. Is that possible to have non-integrable function? And the answer is yes. There are non-integrable functions, okay? And the example that we usually study is the called Dirichlet function. And this is the function that we define Dirichlet function in the interval 0, 1. And we put this function to be 0 if x is not a rational number, and 1 if x is a rational number, x belonging to 0, 1. And this function, 0, 1, it's impossible to draw the graph of this, okay? But just to have an idea, what is this? Is for x rational, the value is 1. Then there are infinitely many values here at 1. And there are infinitely many values here at 0, okay? For each rational number and so on. For each rational 1, non-rational 0, and you have something of this type. Now, is this function integrable? You immediately see that the answer is no. Why? Because you take a subdivision, okay? Take a subdivision of the interval as you want. And now, what is the function? What is this function that, approximate the function by below? Okay, what is the function that approximate by below? What is the rule? The rule is, I have to look for a G belonging to S minus. And what is this? I divide, suppose in this way. Take the first interval. What the value of G? Is the inf of the values of the function in this subinterval. And the function in this subinterval has only two values, 0 and 1. Fine? Then the inf is 0. Sure? The next one, the inf same is 0. The next one, 0. Then the function that you can use for approximating by below is constantly 0. Fine? Then this is a step function, constant, constant, constant. The integral on 0, 1 of my G is 0. If you do the same from above, what you get as plus. And now you consider this interval, okay? The function has two values, 0 and 1. And the sup is always 1, okay? The same for the other, the same for the other. Then my function will be 1. And the integral of 1, 1 is a constant, and then the integral is simply the value multiplied by the length is 1. Okay? Then, if you choose this partition, the G as integral 0, the H as integral 1. Now the question is, but what happens if I choose another partition with many more points? What changes? Absolutely nothing. Because in each subinterval, you find what? You find points where the function is 0, points where the function is 1. Okay? And then the lower integral for my function is 0. The upper integral, being always the integral of a function that is 1, is 1. Okay? And then function of this type is not integrable. Okay? There is no integral for this function. And this is an example that the definition of Riemann integrals, okay, the Riemann integral, doesn't cover functions of this type. Okay? Doesn't cover, this is impossible to define the integral of this function according to Riemann. Some of you will see in the future that the Lebesgue definition of the integral, in this case, give me a definition of integral for this function. Okay, and the integral of this function will appear to be 0. And by this is different. Okay? And then we can say we are given a definition of a Riemann integral. Then given this definition, given a class, a set of functions, a class of functions, can I say if they are integrable or not? Okay, because you understand that using this definition from the practical point of view is almost impossible. Okay, then there are, given a class of function, can I say if they are integrable or not? Okay, and the answer to this question is partly yes, and each of these results is a very important theorem. The most important at all is this. If f is a continuous function on AB, then f is integrable on AB. In other words, all continuous functions in a closed interval are integrable function. Okay? A continuous function is integrable. Okay? I said that this is one of the most important results of mathematical analysis. The consequence of this just if f is continuous on the open set AB, okay, and bounded on AB closed, okay, continuous in the open interval and bounded in AB, then this is f is integrable on AB. And third result, that if my function is f, now no continuity, but if f is monotone on AB, then f is integrable on AB. Then the two classes for which these theorems say they are integrable are continuous functions and monotone functions. That clear? Then continuity is a condition for integrability in a closed interval, or monotonicity. Fine? This result may be quite surprising, okay, because you remember that there are very functions that are quite strange, but continuous. For instance, our function that we saw in many different x squared sine over x, x not 0, and 0 at the origin, this is a continuous function. Okay? The function that you remember is with this behavior, infinitely many oscillations near the origin. This function, 0 at the origin, for instance, if you ask, is this function integrable in 0, 1? Okay, I think it's not very easy to imagine the answer. The answer is yes, is exactly the previous theorem. Okay, and for instance, this function, the terrible function sine 1 over x, the one with infinitely many oscillations, and then you put this 0 at the origin, 0 at the origin, that is the function, this one, with 0 at the origin. This is what? Is a continuous function in an open interval bounded in a closed. And then if you say, is this integrable in 0, 1, the answer is again yes. Okay? And if you imagine this geometrically, and you understand geometrically this, you are very good. I am not able to understand this geometrically, okay, but the answer is correct. Okay, about integrable functions, I will need in 2, then let's say another symbol, the set of integrable functions on an interval AB. We can use R of AB, R for Riemann of AB, okay? R integrable function on AB. What I will need is this result. Then we will simply use when needed. If, suppose, first theorem, suppose that f is integrable on an interval AB. Then I can say that f is integrable on all intervals CD that closed intervals that I can choose inside included in AB. Okay? In other words, if the function is integrable on the big interval, any subinterval you choose, this is integrable on this, on CD included here. Okay? And the next result is if f is integrable on AB, then the absolute value of f is integrable on AB. Then, if you know this, okay, you can say that the absolute value is integrable in the same set. That clear? That theorem. What is interesting to observe is that the opposite is not true. Okay? The integrability of the absolute value does not imply the integrability of the function. And what is the idea for proving this is this. Show an example, obviously. The theorem, you have to prove the theorem. to say that this is not true. Take a function, and you need f non-integrable, but the absolute value of f not integrable. Okay? Since you know just one example of non-integrable, that is the Dirichlet function, the question is, can you modify a little Dirichlet function in order to have an example of this? Very small is not good for this, because the Dirichlet function is bigger or equal to 0. And then f and the absolute value are the same. And then is not. Then you need what? You need a kind of Dirichlet, but non-positive, not always positive. And what is the idea? Is simply take a Dirichlet-like function that is 1 for x non-rational and -1 when x is rational. This function, 1 and -1, okay, is the same as Dirichlet, changing. And this function is non-integrable. If you take the absolute value of this function, the absolute value of this function is the function 1, okay, that is constant, and then for sure is Riemann integrable. Okay, and then you see that this is an example of this situation. Okay, and then we say that according to what we did, we said that if f of x is bigger than 0, bigger or equal, is a positive function, the integral, the Riemann integral over f, over AB of f, is associated with the area of T. Okay? If the function is negative, the Riemann integral will give me the idea of minus the area. Is that clear? If my function changes, if my function changes the sign, what is the geometrical meaning of the Riemann integral? Is the area of this part, taken with a positive sign, and the Riemann integral is minus the area of this. And then this area taken with the minus sign. Fine? Okay, then in these cases, the integral AB of f doesn't give me the idea of area. because is this part with plus and this part with minus. Fine? And then, in order to have really the area of this, positive here and positive here, what you have to do? You have to compute. You need this to be positive, but also this to be considered positive. And then, for the positive part, is not a problem. For the negative, you need something that changes the sign. Okay? And then I have this important result. The area of the region included between the graph of f and the x-axis is given in general, not by the integral of f, but is given by the integral over ab of the function absolute value of x. Okay? If you compute this, if the function is positive, it's fine. If the function is negative, the integral of this will give you a positive number that is exactly the area of this. Okay? While the integral gives you this with a minus sign. If you have this general situation, if you compute the integral of the absolute value, you get what? Look here and here. For the positive part, integral of f, integral of absolute value is the same. Okay? But for the negative part, if you compute the integral of f, you get this area with a minus. But if you compute the absolute value, you get this area with a plus. The area of this equals the area of this, because they are symmetric regions. And then you get the complete area. Okay? Okay, we can stop here.